The Webb look is so far out that getting light has been traveling for north of 13 billion years. Yet, the universe has been broadening, and in this manner, the light has been broadening too. The most far-off universes were recollecting in time, almost to the Big Bang. The massiveness of the universe could appear tremendous. However, each and every piece of it started from what we refer to as the singularity. This is how we could interpret the Big Bang Theory. The James Webb Space Telescope, JWST, has uncovered huge secrets about the birth and advancement of the universe, leaving us confused. Renowned physicist Brian Cox has announced that the critical revelations made by the JWST may, in reality, reshape how we might interpret the universe. All in all, join us as we dive into these new eminent revelations that promise to change our perception. The James Webb Space Telescope, named after the recognized NASA leader James E. Webb, stands as a marvel in current cosmic examination. This telescope represents a colossal mechanical leap forward from its predecessor, the Hubble Space Telescope. Occurring from a collaborative effort between NASA, the European Space Agency, and the Canadian Space Agency, the JWST outperforms the capabilities of its envoy. It uses cutting-edge technology and a design optimized for focusing on the universe in astounding subtlety. Unlike the Hubble, the JWST delivers clear, sharp pictures of faraway celestial bodies, working primarily in the infrared range. This fascinating part allows it to penetrate galactic dust and capture heavenly objects that were previously hidden from our view. With its massive 6.5-meter primary mirror, made from 18 hexagonal sections, the JWST is a far cry from the Hubble's reflector size. Positioned about 1.5 million kilometers away from Earth at the second Lagrange point, L2, it orbits the Sun in a region of congruity with Earth, ensuring a consistent and continuous view of the universe. While investigating the faraway corners of the universe, it involves not just exploring light years, but also a form of time travel. The JWST uses infrared instruments to observe objects and events that occurred billions of years ago. The light produced by these objects, due to the expanding universe, undergoes redshift, moving from the visible spectrum to the infrared frequency or longer. Fortunately, the JWST can detect infrared light emitted by distant celestial bodies at extreme distances, enabling scientists to study the formation of stars, explore galaxy development, and analyze exoplanet climates. Its most recent groundbreaking discovery involves identifying an incredible number of galaxies at the edge of the observable universe, a finding that challenges the validity of current theories about how things evolved, prompting a reassessment of our fundamental cosmological assumptions. To better understand how we arrived here today, we must take a brief journey through the history of space exploration. Early civilizations like the Greeks and Chinese laid the groundwork for understanding planetary movement by observing celestial bodies. Newton's laws in the 17th century provided a theoretical framework for space travel. During the 20th century, Edwin Hubble, an influential cosmologist, made groundbreaking discoveries in cosmology and observational astronomy. His observations revealed that distant nebulae were separate universes, far beyond the Milky Way, altering our understanding of the universe's size and expansion. Hubble's law, established by him, showed that galaxies farther away were moving at higher rates, providing evidence for the expansion of the universe. The post-World War II history of space exploration marked the beginning of the space race, with the Soviet Union's Sputnik in 1957 as the first artificial satellite in orbit. Yuri Gagarin's orbital trip in 1961 and the Apollo 11 moon landing in 1969 were pivotal milestones. Fast forward to 1990 when the Hubble Space Telescope was launched, providing remarkable clarity and extraordinary insights into the universe. The journey from ancient observations to the technological marvels of the James Webb Space Telescope showcases the ongoing improvement in how we interpret the universe. The Hubble Space Telescope, for example, captured the famous Pillars of Creation image in the Eagle Nebula, revealing a star nursery formed by massive clouds of gas and dust. Another significant achievement was the Hubble Deep Field, capturing a vast number of galaxies in an apparently empty patch of space. The Hubble also studied exoplanet climates, pinpointing elements like water and organic molecules in distant worlds, suggesting the possibility of habitable zones beyond our solar system. Following the observation of the nearest known supernova, SN 1987A, it shed light on the life cycle of massive stars. These accomplishments solidified the Hubble Space Telescope's legacy as a cornerstone of modern cosmology, stunning the world with its incredible and vast discoveries. Its successor, the James Webb Space Telescope, was launched to build upon the technological advancements and lessons learned from the Hubble, offering a deeper understanding of the universe's origins, which are still explained by the general theory of the universe's origin some 13.8 billion years ago. The universe began as an intensely hot and dense singularity, rapidly expanding and leading to the formation of matter, energy, and fundamental forces. As the universe expanded, it cooled, resulting in the creation of atoms, stars, galaxies, and the various structures observed today. The theory of the Big Bang also explains cosmic microwave background radiation, light element abundance, and the large-scale structure of the universe. Despite being widely accepted, the Big Bang theory faced skepticism and challenges in its early days. Alternative models, such as the steady-state theory, proposed a universe without a specific beginning. Concerns about evidence supporting the initial singularity, expansion, and observed anomalies emerged. Most of these objections were addressed over time, and crucial evidence came with the detection of cosmic microwave background radiation in 1965, aligning with Big Bang predictions. Space missions like COBE and WMAP, along with technological advancements, further supported the theory. Enter the James Webb Space Telescope, equipped with advanced infrared instruments capable of peering through cosmic dust. The JWST, working primarily in the infrared range, captures the oldest light known to humanity and observes objects formed shortly after the Big Bang. Its infrared capabilities allow it to focus on star-forming regions, cosmic nurseries, and the formation of stars hidden from optical telescopes. Infrared light, with longer wavelengths than visible light, can penetrate interstellar dust, overcoming a limitation of the Hubble Space Telescope. The JWST can observe cooler objects emitting primarily in infrared, making it ideal for studying phenomena like exoplanets, brown dwarfs, and distant galaxies. As celestial bodies move away, their emitted light waves are stretched, causing a shift toward longer wavelengths or redshift. The JWST's infrared capabilities can detect these redshifted signals, capturing light from the early universe and offering insights into its formation and evolution. Energetic events like black hole mergers or new star births primarily emit in the infrared spectrum, further enhancing the JWST's investigative power. The telescope can explore phenomena that were previously hidden, either physically or perceptual. These ancient galaxies existed only a short time after the Big Bang, pushing the boundaries of our understanding of the universe's formation. This discovery challenges previous models of galaxy evolution and raises new questions about the timeline of cosmic events. The JWST's ability to detect these distant, early galaxies has provided us with a deeper look into the infancy of the universe, revealing the processes that led to the formation of galaxies, stars, and the larger structures we observe today. By observing these far-off galaxies, scientists can now investigate the conditions that allowed the first stars and galaxies to form, offering crucial insights into the early stages of the universe. These findings could ultimately change our understanding of how the universe evolved, including the timeline of cosmic events and the nature of dark matter and dark energy, which continue to be some of the greatest mysteries in modern cosmology. Moreover, the JWST's observations are not limited to just the distant past. The telescope's ability to study exoplanet atmospheres is also a groundbreaking achievement. By analyzing the composition of exoplanet atmospheres, the JWST can help determine the potential habitability of worlds beyond our solar system. This could bring us closer to answering one of humanity's most profound questions. Are we alone in the universe? The telescope's contributions to our understanding of cosmic evolution, the formation of galaxies, and the search for life beyond Earth mark a new era in space exploration. Its remarkable sensitivity to infrared light and ability to look deeper into space than ever before make it an invaluable tool for astronomers and scientists worldwide. In conclusion, the James Webb Space Telescope is not just an incredible technological achievement. It represents a giant leap forward in our quest to understand the universe. It builds on the legacy of the Hubble Space Telescope and opens up new frontiers in cosmic research. As we continue to explore the vast reaches of space with the JWST, we are sure to uncover more mysteries that will challenge and refine our understanding of the cosmos, pushing the boundaries of human knowledge and expanding our place in the universe. Hardly any 100 million years after the enormous detonation during the astronomical first light, the astounding part is that we're uncertain about how such huge designs framed so ahead of schedule in the universe's set of experiences. This revelation could lead us to re-evaluate our comprehension of the development and evolution of system worlds in the early universe. Concentrating on early worlds is critical for disentangling the secrets of vast beginnings. The JWST can acquire bits of knowledge into how cosmic systems, stars, and planetary frameworks emerged and developed over billions of years. These perceptions likewise add to more extensive inquiries about the major idea of the universe, including its composition, structure, and the forces overseeing its development. While the Hubble Space Telescope was notable for its time, it had constraints in noticing the early universe. Its principal constraint was its failure to infiltrate really grandiose residue and recognize the infrared light radiated by antiquated systems. More established telescopes depended on apparent and bright light perceptions, making it testing to investigate the early universe, where these frequencies are ingested or contorted by interstellar residue and gas. The James Webb Space Telescope, JWST, addresses a critical jump forward in noticing systems from the universe's beginning phases. Dissimilar to its ancestors, the JWST can notice divine items that framed within a scant few 100 million years after the huge bang. Utilizing its infrared responsiveness and high-level imaging capacities, the JWST has uncovered a wealth of old cosmic systems, offering exceptional lucidity and detail in figuring out the universe's developmental history. Starter results from JWST perceptions have mixed waves in laid-out cosmological models. The definite information challenges a few parts of winning hypotheses, provoking cosmologists to rethink basic standards administering how we comprehend enormous development and construction. Errors between noticed information and hypothetical forecasts have ignited serious discussions inside the logical community. JWST perceptions have uncovered a larger number of cosmic systems in the early universe than expected by existing models, suggesting a more complicated and rapid development process. Some noticed early universes show up more created than anticipated, testing customary models, foreseeing slower advancement. The disclosure of an inconceivable mass of systems challenges the accepted distribution and plan of huge designs, uncovering a more many-sided and denser grandiose web than recently thought. These perceptions bring up captivating issues and roads for additional investigation. The presence of huge designs difficulties early models of infinite construction and arrangement, provoking specialists to refine models for a better clarification. Grasping how such tremendous designs assembled quickly after the enormous detonation presents a riddle that requires a clarification that doesn't abuse central standards of cosmology. Critical variations in the states of the early universe, contrasted with forecasts in view of existing models, have additionally been uncovered. These distinctions could propose already obscure actual cycles, surprising circumstances, or unidentified astronomical peculiarities. In straightforward terms, these varieties have incited researchers to re-examine and work on our models of the universe. Presently, there's nothing left but to say that further investigation is expected to integrate these astounding perceptions into a more exhaustive comprehension of the universe's beginning. Perceptions frequently give invigorating brief looks into the universe. However, in-depth examinations once in a while reveal contrasts. For instance, early perceptions might show explicit properties or courses of action inside far-off cosmic systems that, upon closer assessment, reveal variances in their composition, structure, or transformative pathways. In conclusion, huge peculiarities are extraordinarily perplexing and require cautious examination for us to precisely grasp their real essence. Spectroscopy, a strategy that unwinds the properties and history of heavenly objects, is a model. It includes breaking down the light discharged or consumed by galactic items. By looking at the properties of the light, spectroscopy gives itemized data about the compound piece, temperature, thickness, and development of divine bodies. This examination assists us with grasping the starting points, advancement, and commitments of heavenly bodies to the inestimable embroidered artwork. The JWST has uncovered various cases where starting perceptions contrasted from later examinations. For example, starting perceptions of far-off systems recommended a basic design fundamentally overwhelmed by lighter components like hydrogen and helium, in accordance with hypothetical assumptions. Anyway, spectroscopic examination utilizing the JWST showed entrancing varieties in natural marks, recognizing heavier components or mixtures already undetected or misjudged in the early universe. This difficulties ordinary thoughts regarding the early universe's compound piece and the instruments answerable for their turn of events and scattering across immense distances. Also, beginning suspicions about worlds in the early universe were in view of starter perceptions, proposing a moderately uniform example of improvement and association. Anyway, more point-by-point examinations by the JWST uncovered a substantially more different and complex exhibit of compound organizations within these worlds. The James Webb Space Telescope, JWST, keeps on reclassifying our comprehension of the universe by shedding light on recently stowed away corners of the universe. One of its generally astonishing capacities is its capacity to study exoplanets in phenomenal detail. By examining the climates of planets circling far-off stars, the JWST can distinguish significant substance marks, such as the presence of water vapor, carbon dioxide, methane, and other organic intensifiers. These discoveries give significant bits of knowledge into the potential livability of exoplanets and the conditions that could uphold life beyond Earth. Notwithstanding investigating far-off universes, the JWST is changing how we might interpret star development. It can notice the introduction of stars in locales where youthful stars are encircled by thick billows of gas and residue, which optical telescopes can't infiltrate. With its capacity to recognize infrared light, the JWST catches the slightest flickers of these new stars as they rise up out of the obscurity, offering a more clear picture of the cycles that lead to star and planetary framework development. By examining these districts, cosmologists are acquiring a more profound comprehension of how stars like our Sun appear and advance over the long haul. One more surprising part of the JWST research is its capacity to peer into the hearts of systems. Dark openings, especially really gigantic ones, are accepted to live at the focuses of most huge worlds. JWST's progressed instruments permit researchers to notice the way of behaving of issue around these dark openings, giving new bits of knowledge into their development, their effect on cosmic advancement, and the strong planes of energy they produce. These discoveries are assisting cosmologists with sorting out the story of how universes and their focal dark openings advance together, impacting each other's development. Additionally, the JWST's revelations